Alright, welcome back everyone. In this video what we're going to look at is this idea of beam design, and really what we're going to look at in this class, or for this lecture for beam design, what we're talking about is getting the right sized I-beam for some loads you're trying to support. So in general, 99% of the time, or probably maybe 95% of the time, beam design is going to be based on that idea of a bending moment. We talked about this before, right? So, and that's going to be the process we're going to use, is we're going to base it on the maximum bending moment, and as a check afterwards, what we could do is make sure that our beam is strong enough in shear. We talked a little bit about shear, and also make sure that it's not going to deflect too much. Because of course, even if it can support these loads, if we end up with a beam that is very saggy in the middle, that would not be too kosher, right? Now in this video we aren't going to check shear or deflection. We're going to do that first step of just picking out our beams, sizing an I-beam. And this is once again based on that bending stress. So remember bending stress. With this bending stress equation, we said we had sigma, which is our axial stress. Once again, if we're bending, then it's compression on top, tension on the bottom. So that stress we said was equal to mc over I. And with that equation, the bending stress is equal to m, which was the maximum moment on the beam, c, which was the distance from the center of the beam up to the top or bottom, basically half the height of the beam, and then I, which is called the moment of inertia, resistance to bending. We had an equation for that, 1/12 bh cubed. So with that in mind, what I can do is I can rearrange this equation by, let's see, multiplying the left-hand side by I and dividing by C, and then moving my stress to the other side to give me something like that. So same equation, I've just done a little algebra to rearrange the equation. And the reason I did that is because I am going to define a new variable. And this new variable is called the section modulus. We're going to designate as an S. And we're going to say that our section modulus S is equal to the moment of inertia divided by this C value. And the reason we're doing that is when we were to look, if we were to look at a I-beam, I already know that we have this C value is that distance right here, and then moment of inertia, well, for an I-beam it isn't exactly 1/12 bh cubed, but we could look it up for each individual I-beam. The point being is those are given quantities for any I-beam, so any I-beam will have its own S value. But regardless, so now I can rewrite, or I can look at how that changes our original equation. Substituting that S for the I over C, I end up with a section modulus is equal to the maximum moment, or just we'll just say moment for now, over the stress. So once again, within this equation, what M is the maximum bending moment. And units on something like that could be kip feet, if your measurements are kips in feet, or it could be kips in inches, and you end up with a moment of kip inches. It's always going to be a force times the distance. We could have pound feet, or of course we could have pound inches. It's much better if we can work in inches instead of feet. So if you're given something in feet, multiply it times 12 to put it into inches will make your life easier. As a reminder, to find this value, we in this class are only looking at two different scenarios, and we can use those moment equations. And we had two of them, one with this point load right at the midpoint of the beam. We said our max moment is PL over 4. The other one with this distributed load, a load across the entire beam, which gives us a maximum moment of WL squared over 8. So we can use those two equations to find out what we plug in for that M value, right? Well, what about this sigma value? Well, sigma is something that can be looked up in a table, but if I were to define it, we're going to call this our allowable stress. What that means is it's you know, it may not break the beam or break the material or go beyond that yield limit. Usually it is the yield stress. But it'll be a value that'll either have to be given in a problem or we can look up in a table, because it'll strictly be based on the material of that beam. For example, if I knew this beam was made out of A36 steel, a characteristic of A36 steel says that our sigma yielding stress is 36 KSI. So I guess I could look that up in a table, but yeah, or it'll have to be given in the problem. So let's take a moment and refresh ourselves on what an I-beam is. So as an example, you might see something that looks like this, W6 by 12. And the way the naming works on an I-beam, this first number here is the depth of our beam. And the second number, the 12, represents the weight per linear foot of this beam. So for this W6 by 12, I know that this total depth here from the top to the bottom is 6 inches. Now it's approximately 6 inches. There is, just like a 2 by 4 isn't exactly 2 inches by 4 inches, we have this nominal. So this is a name to 6 inches. It's approximately 6 inches. It might be 5.9 or something like that. But so nominal versus actual. But the weight is definitely for certain. So we know that we have 6 inches deep, and we know that this beam would have a weight of 12 pounds per linear foot, at least if we're still dealing with the W6 by 12, right? So that was a little bit about the I-beams. There are sources out there. This is from the AISC, the American Institute of Steel Construction, and see how long this takes to pull up. In here you can go to this thing called a shapes database. In the shapes database, we want version 15, I suppose, and it's going to download this Microsoft Excel document. Open up this document, and on the first sheet we have this disclaimer and some what everything is turned. But what I care about is down here with these tabs, this database tab. If I look here, I have all these I-beams. So I have a W44 by 355 up top. They're going from heaviest to lightest. I mean, that thing weighs 335 pounds for just 1 foot. So that's a big beam, but it's also 44 inches deep, right? I can tell that just from that nomenclature. But and there's all sorts of information in here, more than probably what we need right now. However, there should be right there, see if I can write on this, I can't. Right about here, there's this thing called SX. That's that new variable we just defined, section modulus. The X means it's about the x-axis. So basically it just means that our beam is, you know, this is our x-axis. It's our strong direction. That's the way beams will always be used. I don't know why you'd ever put an I-beam sideways. Then you'd have to use this SY value. But SX is what we're looking at, right? Now that is a very big table, and it's a great resource if you ever need it. However, just for demonstration, I think what we're going to use in this class is a much simplified, smaller table. So same idea with this table, but I can see it's just 2 pages. It starts with the W24 by 104 and goes smaller and smaller and smaller until you get a W6 by 9, right? Once again, I do have this S value, and I'd be looking at this SX column. So that's the most important column with this new thing. Some other variables we have the area. Of course, that's this, you know, total area of this I-beam. We have the depth. Remember, the depth isn't exactly, so W24 is a little bit off from 24, 24.06. We have web thickness. This is the thickness of the web. We have the flange thickness, BF. That's this guy right there, right? That's right here. So it even tells you this is all for the flange. Flange thickness, of course, that would be, well, it's showing up here, I suppose, right there, the thickness of that guy up there. And then we have I. We talked about I before. It's this idea of a moment of inertia. So I could just look up I values for I beams, because before we said it was 1/12 BH cubed, and that's great if you have a rectangular section. but I-beams aren't rectangular, so I have these multiple shapes, and it gets a little more complicated, so we can just look it up in a table what its moment of inertia is. R is radius of gyration. We aren't going to talk about that in this class. So let's take a look on how we would actually size an I-beam now that we have all this information with an example. All right, so here's my example. I'm given that I have steel with a sigma of 50 kips per square inch. That's the most common material used for steel nowadays, so I figured we'd pick something we actually use. And that's our yield stress. That's the maximum stress. We could call it allowable. It's what we're going to design with, right? We need to support a distributed load of 1.67 kips per inch. Watch your units. Okay, so kips per every inch, we have 1.67. It's 1.67 thousand pounds for 1 inch, so it's quite a bit of load, over a span of 10 feet. We want to find the lightest I-beam from the tables above that would support this load. So I'm going to start by drawing a picture of our loading scenario. Here's my beam. And we have a load up here of let me write it in actually with the little w. Our distributed load is 1.67 kips per linear inch. And I know that this total span here is 120 inches because it's 10 feet, right? And like I said, it's easier just to keep everything in inches from the get-go. That way I don't have to worry about conversions and things, right? So the first step would be, what is the maximum moment? And the maximum moment, we know from our equations, this is a distributed load, so I have an equation for that. And that equation says that it's equal to the distributed load times the length squared over 8. All right, well, plugging in what we have, our distributed load is this 1.67 kips per inch. The total length is 120 inches. That's what I'm squaring. That's where my units work out great because I'm using in inches. Divided by 8. If I plug all that into my fancy-dancy calculator, I ended up with 3,006 kip inches. So you could follow your units through if you wanted to, or I just know that a moment has to be a force times the distance. So I have this kip inches, right? So now I can come up with this new variable. What do I need for a section modulus? So a section modulus, we said, is equal to the moment divided by our stress. Well, the moment I just found to be 3,006 kip inches, and our stress is 50 kips per square inch. So putting that in my calculator, I ended up with something like 60.12 inches. If you follow your units, you'd find out you'd have inches cubed. So what does that number mean? This is my minimum section modulus that I need for our beam. And we're using these tables up here. So then the question is, how am I going to figure out what that is? Well, like I said, the values that we're looking at are in this column here. That's our SX. And if we look at how these beams are arranged, what we have are blocks, right? This block up here are 24-inch deep beams. Then we have 18-inch deep beams. Then we have 16. I missed one, didn't I? 16-inch beams. So on and so forth. We have 14s and whatever. But the way that I like to do this, instead of just looking at every single number, because we're not trying to get to the closest S value, we just need a minimum S value, but we are trying to find the lightest I-beam. Well, how do I know the weight of each I-beam? Remember, that's that second number. That's the weight. That top one is 104. Well, as I go down, they're getting lighter and lighter and lighter, right? 104, 94, 84, 76, get lighter, lighter, lighter. But when I jump to a different depth, now they may get a little heavier. 65 is more than 55. But then it goes down again. So that's how they're arranged. So I need to find the lightest of each section is the way I like to think of it. So my lightest 24-inch deep I-beam. So I could start at the top and say, well, this one has an S value of 258. Is that at least 60? Oh, you betcha, it's well over 60. So I go down, and I can see it's decreasing as I go down here as well, and I need to find a value that's at least 60. Well, 114, the very bottom one, is at least 60, so that means that a W24 by 55 is the lightest 24-inch deep I-beam that would work. Now I'm going to repeat the process for my 18-inch deep I-beams, right? So I start at this 117, and I come down until it's at least 60. Well, it looks like I can go to that 68.4 is above, but if I go any lighter than that, it won't work. So I could use a W18 by 40 as the lightest I-beam out of my 18s. What about my 16s? Going down until I have at least 60. Looks like I'm at 72.4. Gives me a 16 by 45. All right, what about my 14s? Same idea. I'm going to go down at least 60. Did I say 60? Let me see. I forgot my value here. 60. At least 60. I have this guy right there, which is a 14 by 43. Those are my 14s. There is a second page here. So what about my 12s? I'm going down my, once again, this is the SX section until I'm at least 60. Looks like I have 64. So a 12 by 50. What about my 10s? Well, this is unfortunate. Look at this guy, 60.0, and I needed 60.1. This is one of those judgment calls. It's like, is that enough where you could say it's good enough? As an engineer, you know, you could always cover your butt and say, well, I'm not going to go. I'm going to make sure it works and go with the 112. That would be a judgment call, I suppose. Or check with your engineer if it's really close, right? What about our 8s? Now I have 60.4, barely made it, so an 8 by 64. What about my 6s? None of them make it because my strongest 6 only has an S value of 16.7. So let's take a look at a summary of what I just did then. So these are all the beams I just underlined that worked for each depth: 24 by 55, 18 by 40, 16 by 45, 14 by 43, 12 by 50, 10 by 100, and an 8 by 67. Which one is the lightest? Remember, I'm looking in this column over here and saying, what's the lightest out of all those? It ends up, it is an 18 by 40. So what I would want to do is use a W18 by 40. So that's how these things work. Look it over. Let me know if you have any questions or comments. And good luck sizing your beams. We'll talk to y'all later. Thanks.